advanced topics in simulation modeling of EM problems, and we'll have some hands-on training. Okay, so I'll start with high-frequency analysis and the reason and the rationale for doing high-frequency analysis. As everybody knows, electronics and wireless technologies, have been constantly pushing this the envelope to higher frequencies and higher frequency bands. For example, the first Pentium P5 processor that came out in 1994 was 60 megahertz. Had a clock speed of 60 megahertz. Today we have Ivy Bridge that is almost 4 gigahertz, and at this frequency or clock speeds, everything becomes like electromagnetic, and we are going to have wave propagation effects, and wave delay and wave attenuation. All kinds of electromagnetic effects start to show up and become dominant physical phenomena. So whether you increase the clock speeds or you ask for higher bandwidths, either case you end up in higher frequencies. And once the frequencies go high, you need electromagnetic analysis. So some of the applications of electromagnetic analysis are wireless technologies, like a classic, application, and high-frequency analog and high-speed digital circuits that are becoming more and more popular. EMC/EMI, electromagnetic compatibility and electromagnetic interference. A lot of times you have devices that interfere with each other, and you have to characterize the coupling between different systems or different circuits and model their interference. Some other traditional applications of electromagnetic analysis is in remote sensing and radar systems, and navigation, guidance, tracking systems, electronic warfare, missile tracking, for example, and some more I would say esoteric applications like radio astronomy and microwave tomography and hyperthermia, like medical applications of microwave radiation. In all of these applications, we deal with electromagnetic modeling of physical phenomena. Just make sure that's okay. Electromagnetic. So, in terms of what type of physical phenomena we encounter in electromagnetic analysis, there are diverse range of this type of physical phenomena. For example, in wireless systems, we deal with antennas, so we deal with electromagnetic radiation, where the antennas radiate signals into the free space, and then we have propagation, wave propagation. For example, the communication channels, where there's going to be a free space or in an urban environment with a lot of scatters. And we also have electromagnetic scattering for applications like radar, that you illuminate a target with an electromagnetic wave, and we look at scattered echo. So these are the types of physical phenomena that we deal with wireless systems. On electronic circuits, we have different types of physical effects which still fall within the electromagnetic modeling. For example, we have transmission lines. The lines, and the pieces of wire or printed circuit board, wires that or traces that we see in low-frequency electronics, they become transmission lines in higher frequencies, and they have wave effects and distributed effects. So the elements are not any longer lumped elements; they become distributed elements. And there are issues like coupling effects. For example, signal integrity. Whether the signals maintain their shape and fidelity when they travel over these transmission lines. And there are issues like parasitics, the coupling and, like unwanted, undesirable, coupling between elements that are, in proximity of each other. And then there are also passive devices like, filters, power dividers, couplers, different types of things that are meant, as an electromagnetic device. These are the type of problems that fall under electronic circuits at high frequencies and require electromagnetic modeling. So we have to deal with electromagnetic fields and waves. And in general, EM fields and waves, they propagate in a, like a cosine of omega t minus 2 pi r over lambda functionality. What this means is omega is our regular frequency, 2 pi f, and r is the distance, and lambda is the wavelength. So basically, what this cosine of omega t minus 2 pi r over lambda means is because of the wave effect, we have a delay or retardation effect, which is proportional to the distance that the wave travels, and also depends on the wavelength at the given frequency. Now this is serious because as you go to higher and higher frequencies, the wave retardation or delay becomes significant and makes big difference. For example, if the wave propagates over a distance of half a wavelength, lambda over 2, a phase delay of 180 degrees happens, which means that basically your maximum becomes minimum, and things can completely change. So the table on the right shows couple of frequencies and the corresponding wavelengths. At 1 megahertz, or say even at 100 megahertz, 100 megahertz, the wavelength is 3 meters. No electronic circuit is as big as 3 meters, so we don't have to worry about wave retardation or wave delay effects. But when you go to high frequencies like 10 gigahertz, 3 centimeter is the wavelength, and when you go to 100 gigahertz, the wavelength is 3 millimeters, right? So half a wavelength, which means 1.5 millimeter, which is well within most electronic circuits, is going to cause a 180 degree, basically a phase reversal. So these are the frequency bands that electromagnetic analysis becomes very important, because your signal is not going to be able to reach its destination instantaneously, but it takes time and it goes through retardation effects before it gets into the destination. So for free space propagation, the propagation factor, so to speak, is e to the j omega t minus 2 pi r over lambda over r, which means that as the wave propagates in free space, you have delay effects, which comes from the phase delay, but you also have power attenuation, and the attenuation goes as 1 over r squared. Now on circuits, the propagation has different shape, different form. It goes as e to the j omega t times e to the power of minus alpha z minus j beta z. Beta here is the propagation constant, which is 2 pi over lambda effective, and beta, the propagation factor, is what causes delay effects. But we also have losses, e to the minus alpha z, and the losses basically are depending on the type of the transmission line, and as wave propagates along the transmission line, it experiences attenuation. Its power drops. Then we have other effects. For example, dispersion, which is very important for high-speed digital circuits and directly addresses the signal integrity. And the reason for this is your propagation constant, or your effective wavelength, is a function of frequency. If you have a singleton signal, so a sinusoidal, for example, so it's going to be okay because it has single frequency. But when you are sending a digital signal, which consists of pulse, zeros and ones, it's not single mode, it's not single tone, it's not single frequency. It has a large spectrum of frequencies. It's broadband, and because of that, the lower frequency content experiences a different propagation constant than the higher frequency content of your pulse. Therefore, as the pulse propagates along your transmission lines, it changes its shape. It basically loses its fidelity, and what you get at the destination, which is going to be another part of your circuit, is not going to be the same 0 and 1 that you sent. depending on what kind of thresholding you establish. So these are the important things that happen, and electromagnetic analysis can address this type of effects. Similarly, crosstalk and coupling effects, when you have proximate lines, and you may have coupling from one line to another. And then there are also other electromagnetic effects like propagation material media. These days you have probably heard about metamaterials, and these are engineered materials or artificial dielectric materials that have some very interesting properties. Or propagation in anisotropic materials, nonlinear materials, gain media. For example, a lot of optical devices, optoelectronics, we deal with propagation of electromagnetic waves inside nonlinear media. Now, all of these things have said, Maxwell's equations are the governing bottom line, underlining physical equations for all electromagnetic problems. So if you remember from a basic electromagnetic course, Maxwell's equations have a differential form. The divergence of D and B vectors, displacement and induction, are 0 and rho, and then the curl of E and H are related to minus derivative of B and derivative of D, respectively. So these are basically Ampere's law, Faraday's law, and Gauss' laws. The differential form of the Maxwell's equations can be cast into an integral form, and if you remember from all the theorems of vector calculus, so in this case you express the electric and magnetic field over a volume or over a closed surface or over a closed curve. The electromagnetic modeling problem at the end of the day basically reduces to a partial differential equation as a boundary value problem. So you have equations to solve, partial differential equations to solve, subject to boundary conditions and initial conditions. So one of the most popular ways of solving Maxwell's equations is to cast them into wave equations, like wave equation for the electric and magnetic fields. If you are dealing with time harmonic fields, as we do in frequency domain analysis, so you basically pick a single frequency and you assume that your fields have sinusoidal dependence, then you can derive Helmholtz equations, which are like special kind of wave equations. And in this case, we have shown the Helmholtz equations for both electric and magnetic current sources. So, solving Maxwell's equations is not an easy task. Only a few EM boundary value problems have exact solutions or analytical solutions. So, analytical solutions in some cases are simple mathematical formulas, but in most cases can be infinite series, infinite sums of, like expansions. But still they are analytical, so you can express in terms of mathematical expressions. But there are only few of them. Like, one of them is wave propagation in hollow waveguides, like a rectangular waveguide. Another one is plane wave incidence on a layered substrate. The solutions are not closed form, but they are iterative, and you can basically mathematically express in an algorithm. Radiation from a small dipole antenna is another canonical problem that has analytical solutions, and here at the bottom right you can see a small dipole that is radiating. The blue lines are the electric fields and the red lines are the magnetic fields. Or wave scattering from an infinite cylinder or a metallic sphere. Again, you can express them in terms of spherical wave functions or cylindrical Bessel functions. So these are only just a few canonical problems that have closed form solutions. The rest of them you have to solve numerically, which means that you have to have a computer simulation program, to kind of address the numerical solution of the electromagnetic problem. So there is a whole field called Computational Electromagnetics, CEM, that deals with numerical solution of Maxwell's equations for all sorts of boundary value problems. So the computational electromagnetic techniques are divided into, in general, they're divided into three groups: quasi-static methods, asymptotic methods, and full-wave methods. Quasi-static methods are usually for low-frequency applications, and what happens, you reduce the Maxwell's equations to Laplace and Poisson equations and solve them. So usually they are not depending on time. Asymptotic solutions on the other extreme are useful for high frequencies. So you assume that your Maxwell's equations reduce into some sort of quasi-optical form, and you use geometrical optics or physical optics or a similar type of technique. But the focus of this presentation is on full wave techniques, which are more general and they don't have limitation on low frequency or high frequency. In full wave techniques, we discretize the dynamic form of Maxwell's equations, basically Maxwell's equations that are dependent on three space variables x, y, z, and time variable. And we solve one of the forms of Maxwell's equations, either wave equation or Helmholtz equation, on a fine mesh. So basically you discretize your computational domain into small cells, and you solve Maxwell's equations on this grid. And what happens is, by discretizing the computational domain, we basically reduce the Maxwell's equations into a set of discrete equations, finite difference or integral equations, and then we solve them numerically. So in the last 3 decades or so, since early 70s, a large number of electromagnetic simulation tools have been developed. The most famous ones are, they actually categorized or classified either in terms of solver type or in terms of computational domain. So for example, in terms of solver type, they are divided into differential-based techniques and integral-based techniques. In differential-based group, we have finite difference time domain, very popular simulation technique, FDTD. We have finite element method, FEM. We have frequency domain finite difference, FDFD. We have transmission line method, TLM, and a couple of other less widely used or less popular techniques. On the integral-based group, we have method of moments, which is very popular and computationally very efficient. And some people also divide the computational electromagnetic techniques in terms of their computational domain. So you have frequency domain techniques and time domain techniques. In the frequency domain group, we have finite elements, method of moments, FD frequency domain, finite difference. In the time domain group, we have FDTD and time domain integral equation, TDIE, and a couple of other ones. So when we have an electromagnetic modeling, problem, so what do we have to solve and how to solve it? One of the problems that most people have when you have an EM modeling problem is there are so many different numerical techniques, which one to choose. And sometimes it's possible that you may find more than one technique that can solve your problem. For example, a patch antenna can be solved by method of moments, it can be solved with finite elements, and it can be solved with FDTD. Similarly, a bandpass filter, planar filter, can be solved with method of moments, or with finite element, and with FDTD. But different techniques have different pluses and minuses. They have different limitations. They have different levels of modeling accuracy and computational efficiency, structural and material complexity, and geometrical fidelity. So in the next couple of slides, we are going to talk about a couple of these issues. So some guidelines that basically can help us to choose the right method is, well, first of all, depends on what tools you are using. For example, most commercial tools that are available in the market are usually based on one particular technique. For example, HFSS from Ansoft is based on finite elements. So for 25 years they have been promoting finite element as the method of choice, as a solution method. CST Microwave Studio is based on FDTD. So they say that, okay, you can solve everything with FDTD. And similarly, like, momentum from Agilent, uses method of moments and so on and so forth. But what if you have access to many different tools? What if you have access to many different techniques and you can use them? So which one is the best? Here are some guidelines. In general, method of moment and probably more generally, integral-based methods are computationally more efficient. Why? Because they mesh only finite regions of the domain, the objects. For example, if you have a patch antenna, you just mesh or discretize only the surface of the metallic patch and the line that is filling it. As opposed to differential-based methods like finite element or FDTD that have to mesh the entire computational domain. So if you want to use FDTD to solve a patch antenna, you have to not only discretize or mesh the metal portion of the patch and the feed line, but you also have to discretize the substrate, and you also have to discretize part of the free space, or the air region above the patch antenna. There is another issue. Method of moment is naturally formulated for infinite space, and we are going to come back to this, because of using the Green's functions. So we can basically model the entire infinite space using some analytical expressions. But in differential-based methods, you have to emulate the open boundaries using some sort of mesh termination scheme. For example, if you have a patch antenna on a substrate, dielectric substrate, and you have to discretize the portions of the substrate, the dielectric, you cannot just take the infinite substrate, so you have to basically cut it, terminate it somehow into a finite region, and kind of like discretize the finite computational domain. Therefore, you have to use some sort of mesh termination technique, scheme, like radiation boundary conditions, or absorbing boundary conditions, or PML, perfectly matched layers. But on the upside, techniques like finite element and FDTD are more general. They can do much more complex geometries than method of moments. Also, using fast Fourier transform, FDTD can compute a wideband frequency response in a single time domain simulation run. So when you are working with wideband structures like filters, maybe and the method of choice would be FDTD, because with one shot, with one single run, you can get the entire frequency response. On the downside, FDTD has problem with resonance structures, because the energy basically oscillates inside your simulation domain, computational domain, and for resonance structures, frequency domain techniques like method of moments or finite element can handle the structure or the problem more efficiently, from a computational point of view. So these are some of the guidelines that you can use if you have HFSS, or you have CFT Markov Studio, or Momentum, or Emacs, EM.Cube, that has a lot of these different techniques. So there are some guidelines. There are some guidelines that you can use to choose the right simulation engine for a given problem. So since we are running out of time, I'm going to go very quickly over some of the basics of these simulation techniques, and we're going to show some results shortly. Time domain numerical solutions. So here we use finite difference approximation of the derivatives. So we have finite difference approximation of space derivatives x, y, z, and time derivatives, t. Here is the famous Yi cell, or Yi grid. And as you can see from here, Ex and Ey are defined at the edges of this cell, cubic cell, and so is Ez, and H components, Hx, Hy, and Hz are defined at the middle of the faces. So E and H components are shifted by a half cell, and they are interleaved. Also, E components are evaluated at times n delta t, and delta t is a time step. Magnetic field components, H components, are evaluated at times n plus 1/2 delta t. And so this scheme is numerically very stable. And these two equations here show the discretization of the curl equations, where E components are related to the H components, and H components are related to the E components. So we're going to go to an example, and we're going to run a simulation with EM.Cube's FDTD module to see what happens in reality. So here, the first example is a planar bandpass filter on a conductor-backed substrate. So these are basically microstrip lines or line segments. And we are interested in the wideband frequency response of this structure. So we are going to show that you can run this problem both in FDTD and in planar method of moments, and you can see different types of attributes or numerical behavior. So in the case of FDTD, so we have a mesh. As you can see from here, this is the horizontal mesh profile, and this basically goes on top of this. So I have put it up so that you can better see. And as you can see, there are a lot of cells that are on the structure there, and the mesh extends beyond the structure over the substrate. And we are using a non-uniform or adaptive mesh, so that, for example, in the areas that are discontinuities here and here and here and here, you see more cells here to provide a better resolution of Maxwell's equations. The next one shows vertical mesh profiles. Again, around the discontinuities, we see a higher mesh resolution. So how do we excite in FDTD? You have to have a source. And in this case, we use a port, and we use a modulated Gaussian pulse source. So at one port of this filter, bandpass filter, we have put a source that basically is a line or a wire that goes inside the substrate and is connected to the ground on the back of the substrate. And we put a source over there which has a modulated Gaussian waveform. And in order to have a stable numerical scheme, so we have to observe the CFL numerical stability criterion, which means that given the sizes of the mesh size or the cell size in the XYZ direction, you cannot use your delta T arbitrarily. Your delta T has to be smaller than this expression here to provide numerical stability. The other issue in this problem is the mesh termination. Okay, if I go back to the structure of the filter, the filter is on a substrate, but the substrate can go forever. I mean, it can be infinite, so we have to cut it at some point. So here we have a finite domain. Go back one more. So here we have a finite domain, and we have defined a finite computational domain in order to make the numerical solution manageable. And what happens on the walls of this line, I mean on the walls of this box in blue, we apply the perfectly matched layer boundary conditions that mimic the free space or infinite domain. So basically what this means is that when the waves propagate inside the computational domain and hit the walls of the computational domain, in the back of those computational domain walls, there are very complicated anisotropic materials programmed, which are called perfectly matched layers. And they basically absorb all the incident waves at all different incidence angles, and they don't reflect anything back. So the structure thinks that it is infinite. So this is very complicated, but the good thing is, it's programmed, and the user usually doesn't have to worry about these things. So for example, here in this picture, inside the white box is your actual domain. Outside it, which the user doesn't see, are the perfectly matched layers, and kind of like anisotropic materials with 36 material parameters, very complicated. So if we run the bandpass filter, so we see a very nice bandpass response over the frequency. So I'm going to exit the presentation for a second and run EM.Cube. So here is the same structure. So these are like, line 1, line 2, line 3, and we have also the joints. Here. And there are also lines that are hidden. One is here, one is there. And those are the ports. So if I want to look at the mesh, this is the mesh. And I can look at the YZ. So this is called Mesh Profiler in EM.Cube. You can see the structure of the mesh. And the mesh is very important. So even though to examine the mesh every time before simulation. So we make sure that the mesh is correct. And here you see the profiling in the when we define lumped elements or lumped sources. One lump source is put here at the end of or at the back of line 1 or the first line, and the other one is put here. So these are the sources, and we define 2 ports, and now we can run the FDTD simulation. The setting says modulated Gaussian, and so we run this. So we can look at a lot of things, including S11, S21, but per filter, what is interesting is the insertion loss, or basically the filter characteristics, S21. So we look at the plot, and the blue is the phase, and the red is the magnitude. So this is the magnitude of S11. Okay, and you can look at put the crosshair here and measure. Like here we have minus 18 dB and minus 24 dB here. Okay. So we go back to the presentation. So we're going to talk a little bit about frequency domain solutions and method of moments. In frequency domain solutions, in method of moments, we deal with the integral equation formulation of Maxwell's equations. Here, the electric and magnetic fields are related to the sources, which are the electric fields and magnetic fields. In reality, in physics, there are no real magnetic currents out there, but magnetic current is a convenient, theoretical concept that we use in electromagnetics to model slots. So, for example, if your structures has metallic traces, like transmission lines, microstrip lines, we use electric current J. And if we have slot lines, for example, CPW, coplanar waveguide, which is basically like a cut inside metal, or if you have an aperture, a cut inside an aperture cut from a metallic plate, we model them with perfect magnetic conductors. So that's why the M current shows up in the formulation. So the boundary conditions are for perfect electric conductors, we have tangential electric field should be 0. For perfect magnetic conductors, we have continuous tangential E and H fields, basically, across the aperture. And inside the electric regions, we have volume polarization current that is proportional to the electric field inside the region. So these are basically the governing boundary conditions. And in method of moments, what we do is we have unknown currents, whether electric or magnetic. We expand them in elementary basis functions. These are basis functions that are like linear in one direction. So they start from 0, go to maximum and come down in, say, in X direction, and they're constant in the Y direction. So with this type of basis functions, we can satisfy a lot of boundary conditions in planar structures. And if we expand the currents in terms of this unknown, this elementary basis function, known basis functions with unknown coefficients, and we insert it back into the integral equations, so we discretize them, we basically reduce them into numerical or like into a system of linear equations. And so basically your integral equations are reduced into a linear system, and the rest is basically use a solver to solve a system of linear equations. Now you can use direct solvers like LU decomposition, or you can use iterative solvers like conjugate gradient, biconjugate gradient, GMRes, and a lot of other ones. So method of moments has two major parts. First, you have to calculate the matrices, and once the matrices are known, then you have to solve the linear equations. So matrix field process is the first part, linear system inversion is the second part. So let's see what happens if we want to solve the same bandpass filter that we just saw in FDTD, if we want to solve it with the planar method of moments. Here we have a two-port device, similar to the other case in FDTD. And here we have a couple of issues or considerations. In order to model the two-port structure, what we do is we expand or extend the lines, by 2 lambda, so that we get a nice standing wave kind of like pattern. Maybe it's better to show it, in a live demo to see what I mean. Let me get out of this. And here, okay. Now this is similar to what we had before, but in the method of moments, we don't care about we don't mesh the substrate. The substrate is already defined as dielectric of 5 epsilon, dielectric with 5 millimeter thickness and 9.9 epsilon with a PC ground. But when we mesh this, as you can see here, the substrate is not meshed. Only the metal part, this part, is meshed. Therefore, the number of cells is much smaller than compared to FEM, finite element, or FDTD. So you are dealing with a much smaller problem here. That's why method of moments is always computationally much more efficient compared to other differential-based techniques. So if I run this problem, I'm going to see something like this. Okay. Now here you can see the standing wave current pattern that I was talking about. So this is one reason that we are expanding or extending the lines, by 2 wavelengths, so that we can see a clean standing wave pattern. Once we have those standing wave patterns, so we can sample them, we can use Prony's method, which is a mathematical method for exponential approximation of sample currents. And what we do in Prony's method is we extract the dominant propagating modes. So what you see on those lines are a combination of propagating modes which are the TM modes, input and output, and also a bunch of evanescent modes that die away or die off from these continuities. The currents that you get is basically a combination of the currents due to evanescent modes and the currents due to the propagating TM-like modes. And when you take a bandpass filter like that and connect it to a network analyzer to measure the S21, for example, insertion loss, that's what exactly the network analyzer does. It basically extracts the TM waves out of it, and measures the reflection coefficient or transmission coefficient or whatever, as parameters of those TM propagating waves. So Prony's method is very accurate in that sense because it basically mimics what a measurement system does for you. Now here we do the same thing and we get something like this, which is very similar to what we got for the FDTD. The only problem here is that I had to run this problem for 19 points because method of moments is frequency domain. Is a frequency domain technique, so I have to run 19 different frequency points to get all this information, as opposed to FDTD that ran only one time domain and used FFT and basically calculated the whole frequency response in one operation. So as you can see, if I want to do a bandpass filter, even though FDTD's computational domain is much bigger than method of moments, but I would go with the FDTD because in one shot, I can get the entire frequency, and you saw it was so smooth and nice because you got an FFT of the time domain information right there. But in frequency domain techniques, I have to run at each frequency and maybe use some sort of interpolation or adaptive frequency sweep or different types of techniques. But still, I have to repeat it. So there's no free lunch. You can use a time domain. It's bigger in terms of frequency, in terms of computational, but you get a better response at the end. Another example here is a Wilkinson power divider. And the Wilkinson power divider, so we have an input line. You basically want to divide your power equally, from an input port into two output ports. So the power comes from here, signal comes here, and it basically one goes here and one goes to the other side. And you want to make sure that these are matched. You have very little return loss, and you have 3 dB as best, 3 dB power division. So half of the power goes to one line, and the other half goes to the other line. So your S21 should have a magnitude of 3 dB, minus 3 dB, technically speaking. Okay, in this case, we put a lump element. In the planar MUM, you can put a lump element as a combination of RLC circuits with different, parallel and series R and L and C component, connections here. So in this case, we use 105 ohms, for the resistor. And one of the things that you can do, for example, in EM.Cube is to run an optimization. For example, your resistance here can be a variable, like R, that can go from 0 to 1000. R equal to 0 means short, so basically 0 resistance. 1000 becomes 1 kilo ohm, sort of like almost an open circuit. So you can run a parametric sweep and see the results as the value of R becomes bigger and bigger. Or you can optimize. You can say that I want a value of R optimized so that I get S11 almost 0 and S21 equal to minus 3 dB. When we run a simulation of this structure, we get S11 minus 31 dB, and we get S21 minus 3 dB. So that's how you can design a Wilkinson power divider. Another topic of interest in planar method of moment simulation is dealing with vias and vertical interconnects, which you see a lot in electronic circuits, either as signal interconnects or for thermal vias, or for DC lines or different types of things, when you go from one layer of the substrate to another layer. So vias in the method of moments are, at least in 2.5D method of moments that we are using in EM.Cube, they are modeled as vertical currents, and they are modeled as volume polarization currents, and they are meshed using prismatic elements. Now here you can see that the top red is the metal that has been meshed, and then the brown prism here underneath is the via. And in terms of meshing, it's very important that the mesh of the via and the mesh of the metal connected to it are the same, so that it provides continuity of the current from the surface metal to the volumetric via. So volume polarization current is defined to be proportional to the electric field inside. In the case of, so you can do both dielectric materials and metals this way. If you have a dielectric, you just put epsilon there. If you have a metal, then you put, this is a typo, this should be 1 minus j sigma over omega epsilon, and sigma is your conductivity. For good metal, it goes very large, 10 to the 20th or something. For gold is 10 to the 7, or for copper. So you can also do imperfect metals. You can model imperfect metals here too by assigning a finite value for the conductivity. As an example, here we use, we look at, a microstrip patch, and in this microstrip patch, we have a feed line that is connected to a big patch, which is a metal, and then this is on top of a substrate, and with a ground plane at the back of the substrate. When you have no shorting pins, you have a signal that is coming from here, from the right, and it flows into the microstrip, and since the microstrip is, since the patch is resonant at that particular frequency, in this case 2.4 gigahertz, it basically makes it radiate. So you have hot edges at the resonance frequency, and you have pretty much no current on these edges, and you have also very low current in the middle of the patch. So you have basically edge singularity effect here, as you would expect in a resonant patch structure. Now, when we put the microstrip line, when we put the via as a shorting pin here, as you can see, the entire current distribution is disturbed, and it now looks like a more of a circularly polarized, with all edges sort of excited. So this is how we basically what happens here is the same via that we had here. We simply put it underneath the patch, and we run the same project one more time. So from this you get to this. And so that's the way that we do we model vias and interconnects in method of moments. So I'm going to take a break here again and go back to some live demo here. So let's get out of this. So this time we are going to do a simple patch antenna. So this is the patch, this is the line, and this is the port here, and the feed. When I mesh this, I get something like this. Actually, the real source is somewhere here, placed very far from the patch and from the discontinuity, so that it doesn't contaminate. And when we run the simulation, just to show you that how fast it runs. Here you can see very nice standing wave pattern. Okay. In olden days, people were using what was called slotted, it was called slot lines to measure the reflection coefficient. Slotted line, they use to say. So basically, here what we have is, I'm just going on some mouse over here. Okay, here we have maximums and minimums here, the maxima and minima here, And from the information from maxima and minima and their location and their separation, we can find the reflection coefficient. That's what Prahn's method does, as I explained earlier. So we can look at the radiation pattern of this patch. And just to give you an idea that how the you can change parameters here. In this case, if you look at this part, lower right corner of the screen, instead of dimensions for the patch, we put x. X is a variable, so we put the x dimension as x and y dimension as x. I mean, x here meaning for a variable rather than the coordinate. So when I go to my variables, so I have a new variable called x, which has a value of 38, the initial value that I put. Okay, I can now run a parametric sweep, and instead of analysis, which I ran earlier, I can run a parametric sweep and set my variable to start from 36 millimeters to 40 millimeters at steps of 1 millimeter. So this is going to take a few seconds. It's going to be very fast. And here, what is happening here is it changes the size of the patch. I want to make sure that this patch is resonant, which means that it's the imaginary part of its impedance should be 0. Its reactance should go to 0 at that frequency. So if I look at, as you can see here, the size of the patch is increasing. So at the second sample, I'm getting the resonance right there. So that way, I can even show this. S11 plot. Actually, Z11 would be more interesting. Here, what we do is we plot real and imaginary part of the Z11 as a function of x. Here, x is the variable. So x started from 36, 37, 38, 39, and 40. And the imaginary part, let's see. The imaginary part, the blue line, is what we really care about. And it goes, I can put a cursor here and read the values here at this corner. And I can see that you can see that I go from positive to negative. So somewhere there, when x is 38, my reactance goes from positive to negative. So I want to make my reactance equal to 0 to have resonance. So that's how I tune my patch. In this case, I simply ran a parametric sweep. I can use optimization via genetic algorithm optimizations or conjugate direction optimizations to optimize this. Another thing that we can do is we look at the S parameter. Let's see the S parameter as a Smith chart. And again, as you can see, somewhere here, this is 36, 37, 38. I'm cutting the real line, which means that my reactance goes from positive to negative. So these are some design tools that we can use for tuning the antennas. And I think we are running out of time. Paramish, how much time do we have?
It's a 1 hour webinar, Dr. Sabet. So yeah, we're almost running out of time, sir.
Okay, so I'm.
We have a bit of time for we just need some time for Q&A, and then we can wind up.
Okay, very good. Okay, thank you. So I mean, if we had time now, we could show also the effect of the via, but again, you just put via simply there, and it perturbs, the currents, and you can put a bunch of vias here. You can use, like, for thermal vias, this can be, for example, a resistive pad, and you have, some thermal vias, or it can be a DC pad, a bias pad, for example, and you can have some thermal vias there. So depending on the application, you can interpret it as an antenna or as a signal pad, whether it's a circuit or a radiator. So EM.Cube is a software that has a couple of different simulation engines, and so we have FDTD, and we have planar method of movement, we have 3D method of movements, we have physical optics, simulator, and ray tracing simulator. So what it is basically a foundation software, simulation software foundation that has a common CAD and visualization, framework, and many different computational engines can be plugged in. So the advantage of something like this is that most of these techniques require the same type of input and output. For example, you have a geometry. Your patch antenna or your bandpass filter or Wilkinson power divider or whatsoever, they have the same geometry, they have the same dimensions, they have the same material properties, whether you use finite element or method of moments or FDTD or anything else. And usually you look at, you want the same type of response out of these tools. You want S parameter, you want radiation pattern, voltage standing ratio, and things like that. And so what we did was, in EM.Cube, we provided a common, unified, streamlined user interface for all these different simulation engines or different numerical techniques, so that you can build, import, or build your structure from scratch in the same environment, the same CAD environment, and then depending on what is the right numerical technique for it, so you can use certain simulation engine and certain computational module for it. And there are some other architectural issues. For example, EM.Cube has a common CAD modeler. It has mesh generators, simulation engines, databases, and visualization. But what is important is the simulation engines are totally separated from the foundation software. Therefore, your simulation engine can be on a high-performance computing platform. It can be on a Linux cluster, or it can be on a GPU accelerated, like a hardware accelerator, or it can be on anything basically. It can be on a very large mainframe somewhere in National Livermore labs. So you can build your structure in EM.Cube and send the input files, which are all ASCII and open to the user. You can send it over a remote simulation, remote machine that hosts a solver, and you can get the output files, which are again ASCII and ASCII text files, and open to the user. You can get them back and visualize in EM.Cube. Another advantage of something like this is that a lot of complex structures need to be run by different techniques in a hybrid way, basically. Especially system level problems that have different length scales need to be solved by different techniques. So EM.Cube provides a natural environment and framework to use. For example, get your system set up, break it down into smaller parts. One part goes to FDTD, one part is wideband, goes to FDTD, one part is resonant, goes to method of moments, so on and so forth, and so that also creates that convenience. And one more advantage of this architecture is that we can easily plug in new techniques and new simulators. For example, we are working with University of Michigan right now with Professor Eric Mickelson, and we are integrating some of his extremely fast solvers into EM.Cube because our engines are separated from the foundation application, and you just define the right input and the right output. Basically, you define the API, and you can easily plug in, third-party or external simulation engines into the EM.Cube framework. So as of now, we have a couple of simulation engines or computational modules. We have FTTD, we have planar. We saw examples of FTTD and planar. We have 3D method of moments. We have physical optics and propagation for wireless propagation modeling. And we have also plugged in or integrated some government-owned simulation tools which are parallel. And we have also very recently implemented and integrated the University of Michigan's AIM simulator, Adaptive Integral Method Simulator, which is a method of moment for 3D structures, antennas on platforms, on shipboard platforms, on aircraft, and things like that. And so that's where we stand right now. So here I'm going to bring my presentation to an end, and I guess if there is any questions, I would be happy to answer.
Thank you, Dr. Sabet.